Okay, so let's get started here. Again, if you haven't picked up your tests, the tests are up here. They're in alphabetical order. Please feel free to come up here and pick it up. Today at the very beginning of class, we are going to talk about the test. We'll discuss that very shortly here. Since our last class, I have written a draft of the second test. I guess I'm just getting anxious to write all these tests. And I want to point out to you on the Graded Materials webpage that I have posted a draft of the formula sheet for test number 2. And I recommend that you download it now so that as we're going through this new material, you can use this sheet maybe to help you learn the new material, since obviously there's going to be important formulas on there as well as the important R functions that we will be using. Project number 1, I have listed there that we're going to discuss it during our next class. I'm not for sure if we will or not. I have a draft of the project done. I just haven't decided if it might be better just to wait one more class period before we discuss it. If I do make the project available to you, it will be on the Graded Materials webpage, and I will post something to the listserv saying, hey, the project's out there. Please bring a copy of it, electronic or paper version of it, to class so that we can discuss it on Wednesday. Again, I will post something to the listserv if the project is available before our next class. Let's see. So before we get started here, are there any questions? Okay, so let's talk about tests. As you saw from my listserv posts, there were a large number of very good grades there. 20 students got a B or higher, but unfortunately 7 students got less than a B. And we will talk about that part shortly. There are a few things I want to bring up regarding the test to potentially help you do better in the future, if needed. Let's see. So I'm going to take a look at the answer key here. So if you have a copy of the answer key, you can take it out if you want to. So the reason why I'm going to go over some of this stuff here is because I want to make sure the same mistakes potentially are not made again in the future. And so hopefully, again, this will help you out. Okay. So the first problem that I'm going to talk about here is number 1C. Now, if you remember with number 1, it was basically a regression problem, and you needed to estimate the model and do some other simple things with it. One of the more, I wouldn't say a lot of students missed this, but a number of students did, was this 12C here. And pretty much everyone got the final numerical result correct in terms of what you needed to do. Excuse me. You needed to calculate x prime x. Okay? Where the problem that I was seeing occurred was actually showing me how the results could be found using by hand calculations. In other words, showing me how are certain parts of this x prime x resulting matrix, how are they actually found? And the first time that I saw this particular error, I was like, oh, I was kind of surprised to see it. It didn't make sense to me why it occurred. And then I kept on seeing the same kind of error again and again. Well, I shouldn't say a lot of students made it, but again, a sufficient number did that I thought I should bring it up. And this is what I think is the reason why this kind of error was occurring. Okay, so on the formula sheet, I give you an example of how to multiply a matrix A by a matrix B. And so, in order to get the 1 element of the resulting matrix, what you need to do, of course, is essentially take the product of the corresponding elements in the first row of A times the first column of B, and you add them up. Okay? Now, in this particular problem, 1C, essentially, the B matrix here is our X. Now, what threw students off was not realizing that, okay, then I have X transpose over here. So normally when I would take A times B, of course, I take A11 times B11, A12 times B21. Notice the order of the subscripts here. Now since I have a transpose that I'm working with on the left side, my eraser out, essentially what happens then is that this first element, of course, is X11, but the next element is X21. The next element is X31. So that when you multiply by then the corresponding values of X itself, we get X11 squared, X21 squared, and X31 squared. So the subscripts, what I was seeing was that students were saying, okay, it's X13 times X31. Well, that's incorrect. You're simply plugging in X where we saw A and a B. You have to take into account how this matrix multiplication is done with the fact that you have a transpose of the matrix. So, okay, so let's take a look at number 3C. (3C) asks, what is an advantage to using 10R or RStudio for writing a program rather than using the program editor already in R? Okay. So, this right here is the program editor. This is where you can type commands and execute all the commands at the same time. This is the R console window. What a number of you were doing was answering the question as if I had asked it, comparing, let's say, RStudio to the R console window. It's a minor thing, and those of you who did do the R console window, you got the question right if the question actually asked the R console stuff, but it didn't ask for the program editor, so I needed to take off points. One of the reasons why I bring this up, and this occurs in any other class when you're taking a test, is again, you just have to be careful and make sure that you understand what's being asked. Don't answer the wrong question. In particular, I see this most often happen with non-native English-speaking students. While I have a sense that they understand what the right answer is, they don't answer the correct question. And it's sad to see, but I will often see this on tests where question after question after question are answered, but the wrong question's answered. And so, again, be careful that you answer the correct question, or the one that's actually being asked. Then on number 3B, and again, you see this a lot on in tests in other classes. Notice that this is, you can say, a compound question. There's actually two parts to it. You need to answer both parts. And sometimes what I was seeing in our tests here was maybe only the first part was answered. Maybe only the second part was answered. That essentially means you lost about half credit for the problem if you only did one of them. And it doesn't matter how I asked the question. If I would have said what is an R package ? And then how can a package be obtained ? I will still often have students not answer both parts. So I will often ask questions like this. There were other questions like this also on the test where there was two things you needed to answer. Please be careful. Make sure you answer both. And again, the reason why I'm bringing this up is so that hopefully this will prevent the same kinds of errors happening in the future. Okay. If you saw on your test a comment such as need more or show your work, please take that into account on future tests, that you needed to put more there. I was lenient this time in grading these kinds of problems, and I will not necessarily be that lenient in the future. And then lastly here, a number of you got number 4 right, the extra credit, so that was good to see. What I had intended, as I have highlighted there, was that you would have all read the New York Times article that was in the homework, and you would have remembered who the authors of R were that were discussed in this article. What I had not realized, and this is fine, a number of you indicated on your test that you found the answer through looking through the R help, which is okay. I just hadn't anticipated that, but hey, that's fine. Okay, so any specific questions about problems on the exam? Anything you'd like me to cover? Yeah. Okay. Now, this by far will be the easiest test of the semester. And so if you got less than a B on this exam, this really, really, really concerns me. And I think if you got less than a B, you need to seriously think about this course and what you are going to do about it. As I said the first day of class, that this first test was going to be a rather low stakes test. It's only 5% of your grade. And hopefully now this test that's worth just a little bit of your overall grade will, you can say, almost be like a wake-up call, and will help you decide if perhaps you have enough background to actually take this course. Or alternatively, if this will help you decide that maybe you need to change how you are studying for this course. Okay? So if you got less than a B, I think of basically you have 2 options. One, drop the course. Okay? Like I said, these tests are not going to get any easier. They're going to get more difficult. This course is offered every fall. I have no idea if I'm teaching it next fall. Hopefully I will, but I have no idea if that's going to happen or not. And you can think of it this way, that you spent just 4 weeks on this course and you can move on. Okay. Alternatively, as a second option, what you can do is, again, radically change how you are studying for this course. If any of you would like to come talk to me about how you could do that, I'd be more than happy to meet with you. Stop by during my office hours, or send me an email to set up an appointment. Okay? Are there any questions? Okay. Well, let's take a look at where we are in this course. So today we are going to start talking about graphics, so plotting. The key thing is that we're going to we have multivariate data, and we're going to try to get as much information as possible out of a plot. In other words, we're going to try to get as many variables as possible plotted all at the same time. That's going to be a common goal here. Some of these plots you've seen before, but I would imagine that there's going to be a number of plots you have not seen before. And if you remember the first day of class, I showed you this, the section materials webpage, and how I kind of categorize stuff in this course. Basically, we have finished section 1, background material. Ideally, it would have been nice for all of you to come into this course with all of this material that I discussed there, but I anticipated that there was going to be at least some stuff that none of you have seen before, and that, that's fine. But that's why I call this background material. That it's basically the material that we need before we can actually get to the heart of this course, the multivariate stuff. Section 2, I have titled Summarizing Data. Perhaps a better name, I think I will change it for the next time I teach this course, would be Exploratory Data Analysis. In other words, what we're going to be doing is exploring our data. Try to find trends that you might see in your data. Try to detect other items that might be you're able to examine in your data. And one of the key aspects here is that we're not going to make formal conclusions about our data. In other words, we're not going to be doing formal statistical inference. We're not going to be doing hypothesis tests or confidence intervals in this section. There's going to be a few small little hypothesis tests we're going to be doing, but not that many. So we're going to kind of informally draw some informal conclusions about our data. And what these methods then allow us to do is perhaps help guide us to particular statistical analyses that will be more formal that one could do to form these formal conclusions. There are four main things then in this section 2 of this exploratory data analysis. Again, we're going to start off with the graphics section here. And then essentially it's not going to work out, unfortunately, as well as I would have liked. We'll take a test over those four, probably just the first three in the end. We'll take a test over this section. So our next test is about a month away. And that will be worth, I think I have on the syllabus, 20% of your grade. You can double check that on your own. Also with this particular section of the course, what you will see is often there will be more than one justifiable informal conclusion that you can make. And so, you know, one person might say one thing about the data, one person might say something maybe a little bit different. The key is, with this particular section, is that you need to figure out how to justify your conclusion. So it's okay that there might be more than one correct answer, but you need to know how to properly justify your conclusion. Okay, so with that then, let's start this new set of notes. So we're going to talk about plots. You know, I guess a good place to start then is, well, why would you even want to make a plot? Well, often one of the first things that you should do is, when you get a data set, is to plot it. And again, the reason why you want to do that is maybe to come up with some general trends that you see in the data. Maybe identify perhaps some unusual things that are happening in the data, like maybe you found an outlier, for example. And these plots also might help you determine, well, where should you go in a more formal statistical analysis? Also, why should you plot your data? I'm going to jump down to 3 here. Is that once you have done some kind of sophisticated statistical analysis, some formal inference procedures, you can use a plot to help explain, you know, why did I reject the null hypothesis? So you can use these plots to help explain your statistical analysis. This is especially useful for those of you who are stat majors, is that when you do consulting with non-statisticians, let's call them subject matter researchers, when you consult with them, often subject matter researchers are not going to fully understand a particular statistical method. And so what can often be very, very useful then is to actually show them a plot that helps explain what this formal mathematical, this formal statistical method is actually doing, and then they'll think, okay, yeah, now I understand what you're trying to say through these formal methods by looking at one of these plots. I have done this many times in the past when the little bit of consulting that I do. I don't have a formal consulting appointment at the university, but when I have done consulting, I have found this to be very useful, and I'll actually give you some examples from my past consulting work. Okay. And of course, statistical methods are very helpful during the formal statistical analysis, such as if you're doing a regression analysis, you could look at residual plots to help make a judgment of, well, is the model fitting the data well or not? Now, what you will note in this section is that there's going to be a lot of R code. And that's just the nature of what we're going to be doing, because every plot that we're going to be looking at, every type of plot, I should say, that we're going to be looking at, has a different function associated with it. Also, what you often have to do is get the data in the correct format in order to actually use a particular plotting function. So you're going to have to do some rearranging of the data, and that often takes some code. So what I recommend that you do is when you see this R code here that we're going to be talking about, is think of it as a template. that you can modify rather easily for your own data that you might be analyzing, let's say, outside of this class or maybe for projects inside of this class. So again, think of this as templates. I never in this class want you to memorize code. You should have a general sense of, if I ask you to do a scatter plot, you should have a general sense of, yeah, I should use the plot function. But I don't expect you to understand necessarily the syntax involved. That's why you can always look at past programs that I've written, or maybe that you have written, to do the plot. Also for this, I'm going to primarily use that serial data that we looked at previously. I'm going to use the serial data to help explain these plotting techniques. And the reason is because it's a small data set. There's a very small number of variables that we're interested in, and that's going to help us then compare from one plotting method to another rather easily. Okay. So the first thing that we're going to do is talk about two-dimensional plots. This is not going to be difficult. If you wanted to plot, let's say, x1 and x2, a simple way to do that is through a scatter plot. We've done that in the introduction to our lecture. But what happens if you have more than two variables, but you still want to look at, let's say, all pairwise combinations between the variables? Well, then what you can do is what's called a side-by-side scatter plots, or what's often referred to also as a scatter plot matrix. Probably most of you have seen these before, but there might be some of you who have not. And so let's look at an example. So with the serial data, if I want to create side-by-side scatter plots, there's a few different functions that can be used. In particular, there's one called pairs, because it's going to give you all pairwise combinations of possible scatter plots between your variables. So x1 versus x2, x1 versus x3, x2 versus x3, and so on. And so let me go over here to 10. I'm going to read in my data here. I'm going to adjust my data for the serving size. If you remember us doing that before. Note that columns 8 through 10 contain my serial fat and sodium values that have been adjusted for the serving size. Also, for some stuff that we're going to do later, I'm going to find my standardized data as well. Okay, so to do the scatter plot, there's that function called pairs. And here's the simple syntax. You say formula equal tilde, put in, how about we just put in sugar, fat, and sodium. We'll only focus on those. Put in where your data is. And this is simply what we get. Okay? So to help explain that then, let me go back over here to Word. What we have here is that notice sugar is represented here, fat is represented here. So if I match those two up, that scatter plot corresponds to sugar versus fat. Sugar is on the y-axis, fat is on the x-axis. So for example, there's a particular sugar-fat pair right there that has a fat content of about 0 and a high sugar content of about 0.45. Okay? Now if I go over to where you see sodium, and if I match that up with the sugar row, we now have the scatter plot for sugar versus sodium. If I look at fat matched up with sodium, I have fat versus sodium. So I have all pairwise scatter plots. Now, that's, you could say, above the diagonal. If you think of this as a matrix, you can think of this as a 3x3 matrix. And above the diagonal, I have those plots that we just talked about. Now, below the diagonal, we basically have the same plots, but they're just a mirror image. In terms of the mirror image of this plot, is this one right here. Now, sugar is on the x-axis and fat is on the y-axis. So in actuality, all you would need is one set of plots, either above or below the diagonal, but both are actually generated. Okay. So the reason why you would look at a plot like this is to see do you see any kind of general trends here? Or is there any strong relationships between the variables? Yes or no? No, really isn't much. And to help us explain that further, here's my actual estimated correlation matrix that we've calculated before. And you can see that the correlations are relatively close to 0. So, when you would plot the data, then you wouldn't expect to see strong linear association, for example. So this is not necessarily a surprise, this plot that we see. Now there's another function R that generates the same kind of plot, but it adds some stuff to it. It's in the CAR package. CAR stands for Companion to Applied Regression. It's actually a name of a book. If you take my Static 70 class, this is one of the recommended books for the course. And associated with this book is a package that the authors have written that has various functions that they use in the book. And one of the functions is called scatter plot matrix. Okay? And you can see that the syntax is very similar to what we've just seen, except for you also get some other stuff on the plot, or you can get other stuff on the plot. reg.line stands for regression line. Do you want a regression line plotted for every pairwise combination? LM stands for linear model, so it's a simple linear regression line. Then we have smooth equal true. Does anyone know what that means? Any ideas? Anybody heard of a smoother before? Essentially, and don't worry about the mathematical or the statistical stuff behind a smoother, other than you can think of it, and you'll see this shortly. It's basically a flexible line that tries to get at the association between 2 points. Okay, and span equal 0.5 has something to do with the smooth argument there. And basically what this is a Loess model, and it takes 50% of your points and it tries to find a best fit line for 50% of your points. And then it goes to another, you can say, window in your plot and tries to find the best fit line for the next 50% of your points, and so on. And on the diagonal, you're going to see some histograms. And so there's the plot. I'm going to jump back over here to Word so I can write on it if I need to. And so we see on the diagonal of, again, if you think of this as a matrix, you see the histograms for the actual individual variables. That's kind of nice to see. The black points, black open circles, are the same points that we saw with the previous function. But the green line there is the actual simple linear regression model. Now remember, the correlation matrix basically had some very small correlations in terms of they were close to 0. So take that into account then when you're looking at this regression model. With these regression models are essentially rather flat lines, indicating that there's not much linear association. Now the red line then is the smoother. And so again, it's a more flexible line that allows you to maybe see potential associations that may exist. So for example here, take a look at the red line there. So what do you think about the potential association? Is there any? Maybe quadratic? Maybe. Well, I'm not making formal conclusions here. So don't immediately go fit a model right now and check to see if there's a quadratic effect, okay? But, this is something maybe we hadn't seen before from just looking only at the points or only looking at a simple linear regression model. The dashed red lines are basically 95% confidence interval bands. Okay. So very simply, those are some scatter plots. Let's talk about three-dimensional plots that we can do. What I mean by that is I want to have at least 3 variables represented on a single plot at the same time. At least 3. And so where we can start off is with simply a scatter plot. where we can plot, again, two variables versus each other. So let's say x2 versus x1. But in order to get a third variable on the plot, how about we change the plotting point in a way that represents this third variable? This is in particular, this is very useful when this third variable could be, let's say, qualitative in nature. Or let's put it a different way, it has a finite number of possibilities. So for example, with the cereal data, maybe I might be interested in a plot of sugar versus fat. But how about we let the plotting point correspond to the shelf number? And remember, when we first looked at this data set, what we were interested in looking at was, when we were discussing it, one of the things that we were interested in looking at was, do grocery stores maybe put certain kinds of cereal on certain shelves to, let's say, increase the number of people who buy the cereal? So it might make sense then to somehow include shelf into a scatter plot like this when you're examining the variables. Okay. So let me jump back over here to 10. So a simple scatter plot. This was, again, the introduction to R notes. Just to review real quick. My x-axis, I'm going to pull out sugar from my cereal data frame. Y-axis, I'm going to pull out fat from my cereal data frame. I'm going to put some nice x and y-axis labels, an overall title to the plot, and I'm also going to plot some grid lines. So this is just a simple plot of fat versus sugar, which we essentially had looked at in the side-by-side scatter plots. And just from looking at that, it doesn't really seem like there's much of a relationship between the two variables. Okay. Well, let's do exactly the same plot, but now let the plotting point correspond to the shelf number. Come back over here for a second. Now, there are three different ways that you could let the plotting point correspond to this third variable. You could change the color of the plotting point. You could change the size of the plotting point. You could change the symbol that's used in the plotting point. So essentially, actually what you could do is plot 6 variables at the same time by changing, 5 variables at the same time by plotting, let's say, x2 versus x1, and then have the plotting point correspond to 3 other variables there. What I'm going to do simply is only look at shelf number, and I really need to choose one, maybe 2 of these different ways to change my plotting point, but I'm going to do all 3, just to demonstrate how you can do it. Okay. So I'm going to do exactly the same code as I had before for the scatter plot, but I'm going to add this little argument here. So anyone know what that does by chance? Type equal n. So a particular plot type. And for Nebraska? No. Basically, it's for the word no. Meaning, set up everything on the plot, but don't put any points in it. Why? Because I want to control how those points look. So let me execute this segment of code here. And there you can see everything but the points. So next what I need to do is create a vector that corresponds to the colors of the plotting points. And again, I want these colors to correspond to the shelf number. Now, if you remember in the data set itself, I guess I can show it to you. In the data set itself, notice the first 10 observations are shelf 1, the second 10 observations are shelf 2, and so on. So to take advantage of that then, what I'm going to do is repeat, that's what REP stands for, repeat 4 different colors, black, red, dark green, and blue. I just picked those because they seem to, you're able to distinguish between them relatively easy. And then I'm going to repeat each of them 10 times. So if I execute that and put the results into shelf.color, you can see the first 10 are black, the second 10 are red, and so on. And I'm going to use this then when I do my plot. I can do a very similar thing for shelf symbol. If you remember in the introduction to R notes, R has a variety of plotting characters that one could use, and they're simply, to access the different plotting characters, are simply numbers. And so I'm going to use numbers 1, 2, 3, and 4 for my plot. And so using essentially the same syntax, remember 1:4 gives me 1, 2, 3, 4. Using this essentially the same syntax, I get shelf.symbol. Okay. Now, I'm going to put my points on my plot. To do that, there's a function called points. The points are going to be at the corresponding sugar and fat values. PCH stands for plotting character. So I'm going to have that correspond to shelf.symbol. COL stands for color. What color do I want all the plotting points to be? Shelf.color. And then CEX. Does anyone remember what CEX stands for? The size, yeah. So, so the size of the point, again, I don't really need to do this, but I'm doing this to help demonstrate the process. I'm going to change the size of the plotting point for each shelf. So the default size is 1. So for shelf 1, I'm simply going to take 1 plus 0.3 times 1. So I get 1.3. So the symbol itself is going to be 30% larger than the default. For shelf 2, I take 1 plus 0.3 times 2, and I get a plotting point that's 60% larger than default. Let me just show this to you real quick. So there you can see first 10 are 1.3, the second 10 are 1.6, and so on. So that finally, when I execute this code, here's my plot. You can see how the plotting symbols have grown in size for the different shelves. The open circle is plotting character 1. So you can see how that is the smallest overall. And of course, whenever you do a plot like this, you need to put a legend on the plot so that you know what each of the symbols represent. So to do the legend, I can use the legend function. I can specify a specific location on my x-axis and on my y-axis. So when x is 0.5, y is 0.08, that's going to be the top portion of my legend. The title of my legend, sometimes you don't need them. I thought it was good to do it here. The title of my legend is going to be shelf. The actual characters in my legend are going to be 1, 2, 3, and 4. If, let's say, in a different kind of plot, you had actual words that represent the different levels that are being plotted, you could just simply combine them in a vector, such as that, if you really wanted to. BTY stands for box type. Do I want a box around my legend? I don't need one, so I'm going to put N for no. The color of the plotting points in the legend, the first one's going to be black, next one red, so on. Plotting characters in the legend, well, 1 through 4. And PT.CX stands for how big do you want the points in the legend? Well, that corresponds to what we have seen in the CEX argument here. So I'm going to put that there. And there we go. Another way that you can get a legend on a plot, and I think I mentioned this later, but I think it's okay to mention it now. If you put, is it 1? Well, we'll try either one. Instead of putting the x and y coordinates there, if you put locator 1, notice how my mouse has turned to a plus sign, because it's asking me to add somewhere where I designate the legend to the plot. So if I just left click, let's say up here in this empty area, you see the legend dropped. So that's just another way to get the legend on the plot that can be useful in some situations. Okay. So this is page 7 and 8. So do you see any trends? And don't look at the answer that's in my comment, my lecture notes. Do you see any trends there? Any unusual things that pop up?
Red points are kind of up and to the right.
Yeah. So the red points, what if I draw a line down here? So the red points seem to be towards the upper half of the sugar values. So the red corresponds to shelf 2. So what is this saying then? Shelf 2 cereals tend to have higher sugar content. And you can kind of think of this along the lines of my, let's say, my original research hypothesis that I had, and that is that these high sugar content cereals are typically placed at an area where little kids can easily reach and pick them off shelves. Shelf 2, if you remember, shelf 1's the bottom shelf, shelf 2 is the next one up. So it's within reach. Anything else? Well, overall, there's, at least in this particular plot, there's not a whole lot more I think you can really see. You notice that there are some points that are maybe a little bit farther away from the rest up there. And so other than mainly the sugar thing there's really not a whole lot more that you can see from this particular plot. Okay. Now, when I created the shelf colors, the shelf plotting points, I took advantage of how the data was arranged. It was nicely arranged so that the first 10 was shelf 1, the second 10 was shelf 2. But in some other situation, when you're taking a random sample, you might not have this nice little arrangement. So how could you get your data in a nice, let's say, sorted manner such as this if you needed to? So how about we first, let's say, unsort our data? Meaning I'm going to randomly put the data in, I'm going to randomly put, let's say, observation 1 into some other spot in my data set. Remember, there's 40 overall observations. So to basically shuffle my data, another way to put it, I'm going to first of all set a seed number so I can reproduce my results. And then I'm going to use a function R called sample, which allows me to sample particular things in my current data set so that I can hopefully rearrange it later. So I sample from the numbers 1 through 40, because I have 40 observations. My size that I'm going to take in my sample is 40. And then I'm going to say replace equal false. What does that mean, you think? I'm sampling without replacement. Okay, because it wouldn't make sense to sample with replacement here and get the same observation more than once. So I'm going to put that into an object called new.order. And essentially what this does, it gives me a new order for my observations. So the first row of my data set is going to now correspond to observation 10. The second row is going to correspond to observation 24. To get that done then, oops, I did not want that. To get that done then, I'm going to take my serial data set, and notice what I'm using for row numbers, new.order. So that if I execute this, put the results in serial 2, and look at the first 6 observations, notice observation 10 is listed first. Observation 24 is listed second. That's how you can simply rearrange stuff in a data set. Okay. So perhaps, maybe when I originally took my sample, perhaps this is the version of the data that I got. And in order to do the same kind of plot that I just did, what I would like to do is sort it now. So if you are familiar with SAS, you would simply use a proc called what? Proc sort. Okay. Well, here's proc sort in R's context. I'm going to use a function called order. Let me show you the results. I'm going to order by shelf. And so what we see here is that I want the first observation in my serial 2 data set. Then I want observation 8, or row 8. Then I want observation 10, or row 10. And what you see here then, cannot type. So let's look at 1, 8, 10. Notice those are all shelf 1. So order allows you to do the equivalent of proc sort. So that then, if I take serial 2 with the new order of the row numbers, put that in an object called serial 3, you can see now that my data has been sorted. If by chance you had, let's say, more than one thing that you wanted to sort by, you just put after the first thing in your order argument, just put a comma, put the second thing there. That's how you do a proc sort, essentially in R. So now that I have this, I can now, again, use the same code that I had done previously. Any questions?
What if we're in a circumstance where there's not a number of samples in each shelf?
Okay. Well, I mean, in that particular case, the easiest way would be then to, if you knew what it was, let's see. You could maybe somehow create each of these colors, let's say, individually. Repeat black 9 times, then repeat red 8 times or whatever. Alternatively, you could do this. There's a function in R called if-else. And notice what pops up. Test. I want to test a certain condition, and if it's true, do this. If it's not true, then that would be for yes. If it's not true, which will correspond to no, do something else. Okay? And so what I can do is something like this. Test equal serial $shelf equal 1. You need the 2 equals there. Because that, in R syntax, it's just syntax, allows you to do a logical comparison. Is shelf equal to 1? Notice that we use equals for other purposes as well, so that's why there's an equal there. And so, if this is true, then let's make this black. If it's not true, what do you think I should do? Another one. So you could do nested if-elses. Now I'll just type this up. I cannot type. Okay. So we'll do red 2, no equal. And I think I have dark green next. And this overall is maybe perhaps the most general way to do something like this. Actually, no, I don't need the last one. So if I execute this code, there we go. So a set of nested if-else statements. That's all.
So would this be better to assign this to a vector and then C-bind that to your data set?
Well, you don't necessarily need to C-bind it to your data set. I mean, normally what I would do is assign it to a vector, just like what I did with shelf.color before. I didn't assign it to a vector here because I was just demonstrating real fast. But this would be a more general way. There's actually even something. If you had, let's say, a lot of different categories. Maybe if I had, let's say, 10 categories here, 10 shelves. There's actually, I can't remember off the top of my head, but there is another way that you could do something like this that's similar to the select case if you've ever used that in a data step of SAS. I don't think we'll ever run into those situations, but there is other options. Other questions?
That was my main question, but is it better than more database management question? Is it better than just do what's your database information bank in R for data set, and that way every time you bring one different, you just do this same steps over again, or do your best to get your CSV file or whatever and shape in Excel? We have things you got to watch out for in Excel.
I think it all. If I understand your question, is that should you do all these things to your data set and then save it out so you can use it again later, or just simply have it in your program and every time just run it? I think it all depends upon the size of your data. If you have a very, very large data set, I would just do it once, save it out, and then read it back in later at some other time point. If it's a simple data set like this, I just do this. And I would try to usually avoid using Excel because the key is that, and this is I think one of the problems that statisticians have with using Excel to do statistics. I mean, it has its use, Excel does. But the problem is you don't have a record of the code that's behind how certain things are being run. And while you could look at every single cell in your spreadsheet to make sure that you did the if-else equivalent correct, here it's just one line of code. It's more easier to see your mistake here than it is in Excel. There have been numerous examples out there of a small little spreadsheet error cause analysis to be wrong. Other questions?
So you can order by two more variables. I mean, it's ordered by the chef, but then also ordered by chef and the ID.
Well, yeah, and if you're talking about, let's say, sorting the data, you know, I mentioned that with respect to here, all you would need to put is another comma after the shelf, and you could put the third or the next variable in there. And that will do the sorting. It's a little bit different way to do sort than what you would see in SAS. Other questions? But the key thing that we do in R often, when you just want to access, let's say, part of your data set, or if you want to rearrange your data set, you focus on the row or column numbers. That's how you do this stuff. You'll see other examples as we go throughout the course. Okay. So that takes us now to page 9. Okay, so we're going to talk about bubble plots. First of all, my 1-year-old son is learning a little, I don't know if it's a song or what it is at daycare, and they do this. They go bubble, 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 pop. And so last night when I was going over my lecture, my wife was looking over my shoulder and she saw bubble plot. She went bubble, bubble, plot. Anyway, perhaps it was kind of getting late at night, so maybe that's why we thought that was funny. But we're going to talk about bubble plot here. And I'm going to show you a quick example of somebody else's bubble plot that I wouldn't be surprised if some of you have seen. This made some national news a few years ago. It was actually in the news media. And when I saw it, I was like, wow, that's cool. A bubble plot has made the news. This is what the plot looks like. What we have here on the x-axis, and for this particular data set that's being plotted, is the income level per person for a country, so average income level. On the y-axis, we have life expectancy. So on average, how long will we expect someone to live from birth? Now, so you can think of it as a simple y versus x scatter plot. But the plotting point itself, in order to get a third variable on the plot, the plotting point itself, the size of it, or you can say the bubble size, corresponds to the population of a particular country. So again, every single point here represents a particular country, their life expectancy at birth, their income level per person on average, and then their population size. So this is set up for, let me just fast forward a little bit here. This is set up starting in 1809. So in 1809, this is, I'd like to know how they got all the data for all these countries. This is life expectancy versus income level per person. So you can see this big red one here. What country do you think that represents? China. Okay? And here's India in blue. The color coding is to get actual fourth variable on the plot. The color coding is the continent. So for example, that kind of orange there represents Europe. Okay? Now the cool thing about this plot is that they've even added, let's say, another dimension to it in terms of this plot will change as a result of the year. And so I'll just play the little video for about a minute and you'll see what happens.
So in Gapminder world here, the situation 1809. Each bubble is a country. The size show the population and the color show the continent. The brown here is West Europe and you can see from the map for the rest. This axis shows health, life expectancy at birth from 30 years to 80 years. And this axis shows income per person in dollar adjusted for inflation and for purchasing power. 200 years ago, all countries of the world had a life expectancy less than 40 years and had an income less than $3,000. Now I start the world. And you can see that the countries with good statistics, they are jumping up and down. There were famine years, there were better years, and West Europe and North America in industrialization started to grow the economy, but health didn't get much better. And slowly health was getting better. And when we came to a situation about 100 years ago, most of the countries of the world had not improved much. It was only this part of the world that was getting richer and eventually healthier and healthier. And between the First and the Second World War, you can see that the difference between the richest and the poorest in the world is just increasing. It was after the Second World War that most of the countries started to change. The green Arab countries here get richer and richer. China is getting healthier and healthier. Now economic growth starts in China also. And the Arab countries, the green ones, they get healthier. And here we are today.
Okay, so you can, again, this is a multivariate data class. We're trying to get as many variables as possible on the plot to tell essentially a story about our data. And so we have life expectancy, income level, population size, location in the world, and then time. So we got 5 variables all on this particular plot. Kind of a cool example of a bubble plot. Now, we're going to talk about how to create bubble plots essentially just for 1 year at a time. So we in this class are not going to talk about how to get the animation done. If you're interested in learning about how to do the animation, Google is a very big user of R, and they actually have their own package that deals with Google Motion Charts with R. And so you can do a plot like this. I'm not going to show you the motion part, though, but you're welcome to take a look at it if you're interested. Okay. Any questions about the plot that we saw? Okay. So let's look at how we can then essentially get at least a third variable into the plot by having the plotting point, the bubble size, be proportional. Okay, sorry if I didn't say that before. It's proportional to a third variable. So if a variable is, has a very, very small size, it's going to be essentially represented by like a speck on the plot. If it's a very large size, it's going to have a large bubble. Okay, so with the serial data then, let me actually jump over here to 10. The way to do a bubble plot is to use a function called symbols. Kind of makes sense, you know, we're really focused on the plotting symbol here in terms of the size of it. So how about we use a function called symbols for it? And so my x-axis, again, I'm going to plot sugar. My y-axis, I'm going to plot fat. Basically, the new argument that we haven't seen before is an argument called circles. So this is going to correspond, I decided to make it correspond to sodium level. This is going to control the size of the bubble. Again, the size of the bubble is going to be proportional to the sodium value. So everything else is the same as what we've seen before. If I highlight the code and run it, this is the plot that we get. And as you can see, it's kind of one big mess. A whole bunch of bubbles are overlapping in one another and stuff. And this is very common to see the first time you do a bubble plot. Typically what you're going to need to do is fine-tune it in some ways to make it more readable, more usable. And so there are two main things to look at. This is on page 10 for fine-tuning these plots. We're going to focus first of all on the first one. And that is you can control the maximum size of the plotting symbol with the inches argument. The default is 1. And it's not quite clear to me exactly what is meant by the inches argument. Is it the diameter? Is it the radius? I've looked at the help. I've looked inside the code of the function. It's not quite clear to me. In the end, it's not really that big of a deal. Inches equal 1 is the default. If you go to inches equal 0.5, that means the largest possible size that a bubble can be is 50% of the default. If you do 1.5, 50% bigger than the default. And you can play around with the number there to get something that looks reasonable. A second thing that you can do, we'll talk about this shortly, is that you can rescale the plotting symbol. So instead of, let's say, plotting just sodium itself, maybe you could do some kind of transformation of it that might help make the plot look better. You'll see examples of that shortly. So what I did in my exact code that I just showed you with the symbols function, I added the argument inches equal 0.5. And now we get something that's a little bit more readable. So again, the size of the bubble, the size of the plotting point is proportional to sodium level. So, what trends do you see in this data? Not looking at the answer in the comment of the notes. It's almost what you don't see. See those little specks there? Those are two observations. Those are observations with the small sodium levels. In fact, they have sodium levels of 0. If you were to do this kind of plot in SAS, nothing would be plotted. So what we've found here potentially are some outliers. Okay? Well, let's figure out what those two observations are. Let me get my plot here. Well, we're going to use a function called identify to help us identify what those observations are. So this is actually interactive, allows you to interact with your plot in a similar manner to what the legend function, when we use that locator 1 part with it. My x-axis, sugar, y-axis has fat in it. And so if I click on that, notice when I come over here to my plot, notice my cursor again is a plus sign, indicating it's asking me to add something to the plot. In particular, what I would like to add is I want to identify what these small points are. So I'm going to click on it, left click, observation 30, observation 26. I can come over to some other points if I really wanted to. Like if I click in the middle here, I get observation 4, 8, and so on. If I click something way out here, notice you get a little warning message saying, okay, there's nothing over there. Why are you clicking there? Okay. Now to stop this, this behavior here, to remove the plus sign, I just right click, bring up that shortcut menu, and left click on stop. And you can see which observations were identified. So let's take a closer look at observations 26 and 30. So I'm going to simply, with my serial data, say I want to only look at rows 26 and 30, and this is what I get. Notice both of them are shredded wheat. If you're eating shredded wheat and look at the nutritional contents, you know that it has no sodium in it. And so these are the outliers that we have identified in our plot. They're also very low in sugar, very low in fat. This is a very good cereal for you. Doesn't always taste the best, but it's a very good cereal for you. I recommend adding some fruit. Eat it. Anyway, so that's kind of interesting. That this is one way to identify what those points were. But let's say instead you want to actually identify all the points at exactly the same time and not have to click on every single one. There is a way to do that. That's it. Okay. There is a function called text. So I want to plot text. In other words, in this case, it's going to be observation numbers. That is actually the default on my plot. So I'm going to create my plot again, and then on my x-axis corresponding to sugar, y-axis corresponding to fat, for my labels, I'm sorry, actually I'm not going to plot the observation. Well, let's actually plot the observation numbers. We'll do that first. That's okay, we can deviate a little bit. So there's all my observation numbers. Now, of course, in these kind of situations, you know, we do have some cereals that are very, very similar to one another in terms of the nutritional content, so that's why you can't necessarily read all the observation numbers there. But you can imagine maybe other situations where, that you could, in fact, read all the observation numbers, and this is what we get here. But let's say instead I wanted to maybe plot the actual sodium content, the actual numerical value. And so we can add an argument called labels. How do I want to label every single observation in the plot? Well, I want to label it with the sodium values. But I want to label it, make it look nice, so I'm going to say let's just round each of these sodium values to 2 decimal places. So let's go ahead and do that. And you can see, for example, here's a 0. If you see where my mouse pointer is, here's a 0. And you can see how those are labeled there on that plot. Those shredded wheats. Okay, so top of page 13, something I unfortunately skipped. So what would happen if we would try to do the same plot, but for this third variable that the size of the plotting symbol is proportional to? Suppose that third variable actually had a mixture of positive and negative values. What do you think would happen? Excuse me? That's what would happen in SAS, but it doesn't happen in R. Any idea? You would get basically a dash symbol versus a solid line for the bubble. So you get a dash bubble. And so what SAS does is essentially says, okay, let's look at how far you are from 0. So if a variable that had a value of 3 or -3 would have exactly the same plotting plotting point size, but the positive one would have a solid line for the circle, and the negative one would have a dotted or a dashed line as its circle. That's what SAS would do. What do you think R is going to do? No. But thank you for the answer. Any ideas? Syntax error. That's what I shouldn't say syntax error. It's going to say, warning, can't do the plot. You have to have positive values. So what would you do in this situation then? If you had this third variable that had potentially negative values, what could you do? Make the variable all positive. So, find, the minimum value for the particular variable that you have. Let's just look at a quick example. So let's say I have -1, 2, 3. Okay, very small data set. And what I need to do is basically make y to be all positive values. So what I could do is take y minus min of y And there you go. So notice it finds the smallest possible value of y. It's -1. And essentially I want to shift everything up. So instead of taking plus it, I need to take a minus it. Because that turns then that minus value for the min of y into a positive value. And so now you could plot then y like this. So it's just a minor thing, but you might run into this kind of stuff for your own plotting purposes. So that's why I want to make sure that you understand that. Let's see. So page 14. So as I said, when you do a bubble plot, often the first time you do it, it doesn't really look very good. You often have to make some modifications to it, do some fine tuning. One way is with the circles argument. Another way is to do a transformation on this this third variable that you're using with circles. So, for example, I did another plot. I left inches the way it was, 0.5. But instead of plotting sodium itself, where did my plot go? There it is. Instead of plotting sodium itself, instead for circles I said square root of sodium. And this is the plot that I get. Compare the bubble size on page 14 to page 13. What do you see happen? I guess I have a question towards the bottom of the page that kind of says what happens, and that is the bubbles are now more similar in size on the plot on page 14. Why does that happen? It's the result of the transformation. Now, in other classes, you probably, especially like a regression class, you often see like a log transformation. You often see a square root transformation to try to make your data, let's say, less variable. Well, what happens then with these kinds of transformations, it makes the variability smaller. And so if the variability is smaller, that means there's less distinguishing qualities between, let's say, the lowest value and the highest value. So thus, then the plotting points in this particular situation will become more similar in size. In this particular case, it's not very useful. But in situations where you have a few, let's say, outliers in terms of very large observations compared to the rest for this third variable, this can be very, very, very useful. For those of you who took, for example, my categorical class, set 875, you saw that as an example when we were evaluating the place-kicking data set. And we were doing some bubble plots with that. So whenever you have a large outlier, this can be very, very helpful to essentially rescale your data. And what I say on page 15 for you to do is try it on your own. So maybe with the serial data set, change a data value for sodium. Now, of course, in real-life applications, you don't change data values. This is when you can do it to help learn how to do this, do these kinds of plots. Change a particular data value, change the sodium value, make it a very large comparison to everything else. Do the plot with circles 0.5, and then hopefully you'll see that one bubble is very large. Then try a transformation, see if that helps you read the, make better sense of the plot. Okay. So I have a question here then, and that is, well, how could you add shelf type or the shelf number to a plot like this? Where's my plot? We'll just go here. So how can I add shelf to it? So essentially then we would have 4 variables plotted. You would what? Can you change the plotting character?
Change the line on the circle.
How would you change it?
Color it.
How about color it? Yeah, how about change the color? I know we're out of time, so I can just show you this real quick. This is the code's not in the notes, but it is in my program. Let's see now. Where is that? There it is. So I created shelf.color just like what I did before, and you would think that there would be a COL for color argument just like what we saw in the plot function. Fortunately, there isn't. Instead, the argument that you want is FG, or actually I don't remember, foreground, I think. Well, trust me, it changes the color. I'll execute it just to show you. Also, I'm doing LWD equal 5 line width so that you can distinguish between the colors a little bit better. So I made the width, I'm sorry, the plotting symbol 5 times, the line for the plotting symbol 5 times wider than normal. And so there you can see that. And then, of course, you would add then a legend to the plot to help distinguish between the different colors. Okay, unfortunately, we are out of time. Are there any questions? Okay, that's it for today.